Hello and welcome to Education at SSBJ. We were into the chapter Sound of Class 8th CBSE. In this video tutorial, we will look into propagation of sound and amplitude of sound. Let us have two wave patterns, and these wave patterns are due to vibrations of different medium. Suppose if these wave patterns are formed within a period of 3 seconds, right? Wave pattern which is on the top as well as the one which is at the bottom, both are formed within period of 3 seconds. You may be thinking, what is the difference between these two wave patterns? What about their frequency? Can you find out what the frequency of the one which is on the top and then one which is below? Well, we shall check what is the frequency of these two waves. Let me take first this wave. Now, what is frequency? Frequency is number of waves per second. Number of waves per second. In 1 second, how many waves are formed? And you know, wave is nothing but movement from initial position, this is complete plane is an initial position. From initial position to extreme position, that we call it as crest. And then another extreme position, what do you call this? Trough. And then again back to initial position, right? From here to here is a one wave. Such how many waves are there? This is number one, this is again another one, second wave, and this one is the third wave, right? So, three waves are formed in how many seconds? 3 seconds. Now, what is the frequency definition? Number of vibrations or waves per second. And therefore, per second we have to find out. Per second means in 1 second. Right? So, 3 second, 3 waves, 3 second, 3 waves. In 1 second, it's a one wave. So frequency is one wave per second, or we call it as 1 hertz. Right? So frequency of this particular wave is 1 hertz. So keep this in the mind. Now we shall see frequency of the second wave. Now here check how many waves are there. As I have told you, from initial position to both crest and trough to here. So from here to here one, here to here another. So this is the first wave, this is the second wave, and this is the third wave. Right? And what is the frequency? It is just like the first wave itself, isn't it? Here 3 waves in 3 seconds, here also 3 waves in 3 seconds. So 3 seconds, 3 waves. Therefore frequency is simple, 1 hertz. Same repetition here. Well, frequency of both the waves are same, but still they are different. Why are they different? What is that aspect which makes them different? These waves are different because their displacement from initial position is different. Let me explain that. The plane surface of this wave, I am just making a mark over it. This indicates initial position of a medium or any vibrating body. From here, it is moving up and down. Right? So from here, this particular part of the medium moves here. So this is from here to here. This is the height which we can call it as maximum displacement. So maximum displacement. So what is the maximum displacement here is this portion. And here it is this portion. Not only on the top. What is the maximum displacement here below? It is here and here. Right? Now look at the maximum displacement of this wave. It is from here to here or from here to here. Right? So these waves differ in their maximum displacement. Right? And this maximum displacement is not only of this first wave, it is everywhere now. It will be above as well as below. And this maximum displacement of a vibrating body, let me repeat, maximum displacement of a vibrating body. In case of this vibrating body, this is the maximum displacement, and down here this is the maximum displacement, and so as all this, that is called amplitude. So what is the definition of amplitude? Amplitude is maximum displacement of a vibrating medium is called amplitude. How does amplitude affects the sound? What you are watching is a wave formation or wave pattern of my sound. You can watch there for every wave. You can locate a height of the wave. Now observe the height of the wave. When I reduce my volume, or sometimes when I am loud enough. So now let me be speaking in a very low volume, and you can watch there the height of the wave is reduced. So amplitude is less here. And when I speak loudly, the amplitude is becoming bigger and bigger. The height, the displacement of the wave is more. So what is the conclusion? Amplitude is related to loudness of the sound wave. Can you compare amplitude of these three swings, which is right on your screen now? You see the first one, it's moving too far as compared to remaining two, which is at the back. So obviously the amplitude of the first one is more. Let us have a brief understanding on propagation of sound. What do you mean by propagation? By propagation, we mean actually a transmission of sound. But transmission of sound through what? Transmission of sound through media. But what do you mean by media? We have around us solids, liquids, and gases. These are different medium. We call solid medium, liquid medium, and gas medium. Right? So these are the media through which sound has to travel. Let us take gas first. Are we able to listen a sound through air? Yeah, very much. We can very well listen. That means sound travels through air. What about solid? Through solid also sound travels. Let us go in detail transmission of sound through solids in next part of video. But remember at this point, sound travels through solid also. What about liquid? Sound travels through liquid also. So sound travels in all the three mediums. Sound can travel through solid and sound can travel to gas, as well as sound will travel through solid. In the air, sound travels in the speed of 343.3 meters per second. So remember this. But this is an approximate value. As the temperature of the air changes, slightly the speed of the sound changes. Again in the water, it is around 1450 to around 1500 meters per second. Almost 5 times than the sound in air. Again, it depends on nature of water. Speed of sound in solid is around 6000 meters per second. It is much more than in water as well as than in air. Now, why the speed is different? What is that property of solids makes a sound to go in more speed comparatively to air and water? Now visualize that the atmosphere in terms of air particles, and it may appear like this. Air particles all around us. And if you can imagine that air particles in terms of air columns in the atmosphere, we can imagine like this. Each column represent the columns of air of the atmosphere. Will make these columns still thin and the atmosphere bit dark, so that we can visualize and try to understand how our sound move through these air columns. I repeat, air columns. Again, to remind you, sound is a form of energy. We blow horn, the sound moves in the air. But how does it move in the air? Just now I have told you to imagine atmosphere in terms of air columns. The moment a person blows horn, the energy transfers to the nearest air column, and that air column starts moving to and fro. And that is what you see on the screen. Now that energy is transferred to the adjacent air column. And now you can see the air column is being moved to and fro because the horn is on. The energy goes from vocal cords of this person through air, and that energy starts moving air column by air column, and then it goes to the nearest air column. All that air particles will start vibrating to and fro, and you will find the energy moves from the horn towards your ear. And what is the direction of that energy? You can have that feeling that energy is moving from one end to another end because of to and fro motion of air column, and you hear that. Suppose if you can take a snapshot of this phenomena, right? Somewhere you can make a pause and take a photo of this phenomena, this vibration. It may be like this, right? Now observe properly. These air columns are appearing sometimes closer, right? You can see that first two air columns, they are closer. In between there is two more, and the last end there is little bit end, there is two more. These two air columns are very close, whereas these are not so close, right? Somewhere here they are close enough. Here they are close enough. Now if you can neatly draw this figure again, you'll get this type of movement of air, and the denser part of the air is called compression, and the rarer one is called rarefaction. So that means in the air, the sound energy travels in terms of compression of medium as well as rarefactions of medium. They keep moving to and fro, and they appear and they form into compressions and rarefactions. So how does sound travels in air? The answer is sound travels in air through compressions and rarefactions of the medium. Right? We know that each of these media are different. I am speaking about gas, solid and liquid. You can visualize that gas particles are a bit away from each other. There is more of distance between them. And since there is more of distance between each of the air particles, the energy which is given to this particle takes some time to transfer here because of the distance between them. So therefore, energy goes little slow here, right? So it takes some time to transfer, and then it takes bit time to reach our ear. So this is about a gas medium. So since the energy takes bit of time, you speak here and the sound travels, the energy goes and hits here, and this starts moving to and fro. It takes some time to reach here. So the sound energy travels a bit slow. How much slow? In gas, the speed of the sound is approximately around 330 to 340 meters per second. So remember this, 330 meters. So in 1 second, sound travels in air approximately 340 meters. Much higher, but not that higher like light. Light travels 3 lakh kilometers in 1 second, whereas sound travels 340 approximately. Again, it depends on the temperature around. But can we compare this to a liquid medium? In the liquid medium, particles are a bit closer. We can imagine that. You can see here the distance between them is bit more, and therefore energy transfer takes place little late, whereas comparatively here they are closer, right? They are closer, a distance is less. Now can you tell me what will be the speed of sound in liquid? Will it be more or will it be less? Why it was less here comparatively? Because it takes time for the sound to move from one end to another end here because of the distance. Here it is slightly lesser distance, so the speed also will be comparatively more. So sound travels around 1450 to 1498 meters per second. Now you can imagine the solid. Will the speed be more in solid? How are the molecules arranged in solid? They are very, very close to each other. Therefore, the sound energy, you speak here, a sound energy can very easily transfer from one particle to another particle because they are very close. Very close. And therefore, you tap here at one end, you can hear clearly here at another end. This sound will come. Immediately you will get that. And very clear sound you will get that. You must have played there in the class. So sound comparatively is more faster than liquids and gases. So what is the speed here? Around 6,000 meters per second. Again, it depends on metal to metal. So where there are particles, there is a vibration. And because of the vibration, sound moves from one end to another end. What about transmission of sound in vacuum then? And what is vacuum then? Is deep space is vacuum? Vacuum is a space where there is total absence of matter. No matter at all. Now can you imagine that what will vibrate there when there is no matter? In case of air, we had air particles to vibrate. So it started vibrating. Right? And we could hear the sound. But what about vacuum? In vacuum, no matter and therefore no vibrations. And when there are no vibrations, there is no sound. And that's why we don't hear sounds of explosions occurred in the space. Right? So here we will conclude. Remember all the contents of this chapter and see you in the next video tutorial. Thank you.